Good afternoon, everyone, and welcome you all to our webinar series. I'm your host, Surathep Kyaohom, coming from Chulalongkorn University, Thailand. I'm glad to see you again in our webinar series today. And this is the last talk in our webinar series. This event is organized by the Energy Storage Cluster, Chulalongkorn University, Thailand. Importantly, the events are supported by the Office of National Higher Education, Science, Research and Innovation Policy Council, and the Program Unit for Human Resource and Institutional Development, Research and Innovation. Today, it is our great honor to have Dr. Phumlani Msomi with us. Dr. Phumlani Msomi is currently a senior lecturer and researcher at the University of Johannesburg, South Africa. His research focuses on fuel cells and batteries, particularly on using nanomaterials to improve the polymer electrolyte membrane and the use of these nanomaterials in the fuel cell catalyst. During the session, if you have any questions, please leave them in the chat box so our speaker will address them later after the talk. Now it is the time that we all can enjoy the lecture. Dr. Msomi, please.
Thank you very much, Prof. Just to confirm if you guys are able to see my slide. Prof? Good afternoon, Prof. I just want to confirm if you guys are able to see my slide.
Yes,
my presentation.
your slide is colorful. It's vivid and colorful.
Thank you very much.
Okay, I'm going to leave the stage.
Thank you, Prof. Kino, for inviting me to this webinar series. I know it's been a series that has been running the entire month of October, so it is my pleasure to be part of this series. As you've correctly indicated, I'm from the University of Johannesburg in South Africa, and my research group and my colleagues, we are working on composite membranes for improving polymer electrolyte in both fuel cell and also in batteries. We're also trying to start adopting using the same membrane for different storage, including supercapacitors. So today my presentation will solely focus on composite polymer electrolyte membrane for fuel cell and battery storage. If you've never been to South Africa, this is just a picture showing you the area or the city in South Africa where I stay in. I stay in Johannesburg, which is why our university is called University of Johannesburg. As you can see on the top right, this is the emblem of the university. This is the side where the University of Johannesburg is situated. So if you are in Johannesburg, the Vodacom Towers, that's what you call it, this tower, it's the monument which should be able to tell you where the university is situated. So I'm from the University of Johannesburg in Johannesburg, and what you are seeing now here is some part of the city of Johannesburg. If we zoom into where we're showing the emblem, this is where the University of Johannesburg is situated. This is the entire campus. As the University of Johannesburg, we have 4 different campuses, and the one I'm showing you currently is what we call Doornfontein campus, which is predominant science campus. We also have 3 different campuses in other areas, but all of them are within the Johannesburg area. So all of this area, as you can see, this section is part of Johannesburg. All of this is part of the University of Johannesburg, which is my campus. So to begin our talk, we firstly want to run through you guys and everyone who's listening about the minerals for energy sustainability that you have in South Africa. Everybody by now is aware that Africa is rich in minerals. It can be South Africa, it can be Zimbabwe, it can be Libya, it can be any African countries. It's a known fact that as Africans, we are rich in terms of minerals. So this is just a map showing how South Africa is rich and some of the material which are now used for renewable energy storage. When you look at gold, you look at platinum, you look at diamond, you look at copper, you look at chrome, you look at iron, you look at lead, you look at manganese, you look at nickel, you look at vanadium, you look at zinc, you look at fluorspar, and so forth. All of these materials are predominantly currently being used in renewable energy. And now they've become rich in terms of their use, because now we can use them in terms of nanomaterial. Historically, we could not use gold for anything in terms of our renewable energy or in terms of our research. But now we've been able to find out that the moment we take this bulk material, we reduce them to nanomaterial, we are able to use them for anything. Take platinum, for example. Platinum has been historically used worldwide for the use in automotive, in cars. And South Africa has been the highest producer of platinum in the world. South Africa currently holds about 90% of platinum that is used in the world. So you can see how rich we are in terms of platinum. You look at vanadium. Vanadium, South Africa is one of the highest producing countries of vanadium in the entire world. So you can see that we need to start using this material for our benefit as South Africa, and also as a benefit of the African countries. Sadly, due to historical disadvantage, all of this material I'm mentioning, we are unable to even get them in South Africa as we are doing research. I'm currently doing research which utilize all of these commodities, but I'm unable to get a country where I'm able to buy all of these commodities readily available in South Africa. We still have to buy them in US or buy them in UK, which is something that we need to change. But that's the politic for another day. Today, I just want to indicate you that this presentation or this type of material that I've mentioned should be and can be used in the development of catalysts for batteries, for fuel cell and supercapacitors. Those are the main components. So imagine if as an African countries, we can start owning this material and use them in these devices. You can see how rich in terms of industrialization and in terms of human capacity will be in African countries. But I will not be talking about the developed catalyst, even though it's some of the work that you do in our group. But today I will be looking at developing of membranes. But also these membranes use this type of commodities or this type of catalyst in their nanoscale to improve these membranes, to enhance properties and be able to use in this different type of energy storage. Like I've mentioned, we want to provide solution using South Africa and African material for African countries. And after that, you should be able to share every knowledge and every commodities, but everything should be started in-house, which is South Africa and Africa as a whole. These are different type of clean energy. All of those material that I've spoken about, all the different commodities I've spoken about, can be useful. If you're looking at this slide, you're seeing that there are different type of energy storage. You have fuel cells, you have hydrogen economy, you have solar, you have hydro, you have electrolysis, you have zinc air batteries, metal air batteries, you have different type of renewable and clean energy storage system, and one which can produce electricity, which most of them are dependent to these material which we already have in abundance as South Africa as an African country, which is why then we're supposed to start doing research which will primarily focus on the material that we have as a country, which is why in my group and my colleagues at the University of Johannesburg, we're looking at what we call supercapacitant, fuel cell, and metal air batteries, which use this type of material. As I've indicated, I will not be looking at the catalyst and the inoma because my presentation today also focus on what we call the polymer membrane within the fuel cell and also within the metal battery. So I'll be looking at how have we designed different membranes and how have we functionalized them and how have we tested them with a use in fuel cells. We're also going to be looking at different type of membrane that we've prepared for solid state metal air batteries and how we've been doing that chemistry. So my presentation is based on material science and also on surface chemistry and also on polymer science. And as you can see, this is the type of polymer that we design. We design, if you have a normal polymer, then we are able to emblem conductive material and also add these precious material. One of the material which we use a lot, it's carbon material and also different type of metal oxide, which are readily available in South Africa, but we will explain that as we go along. So I'll be focusing on membrane as an electrolyte in fuel cell application and also in metal batteries. Again, as you guys should be aware, this work is not done solely by me. It's done mostly by my student. I'm just supervise everything and also make sure that the results that you get are presentable. Let's come to fuel cell. Well, by now, there has been a buzz about fuel cell, not only in South Africa, not only in Africa, not only in Thailand, not only in Germany, but worldwide. Why there has been such a buzz about fuel cell? Well, fuel cell, it's important because as an electrochemical cell, it's able to convert chemical energy to fuel. That's a very important statement, converting chemical to fuel. If you look at the history of fuel cell has been discovered about 50, 100 years ago. The first use of fuel cell has been on the Apollo space, where it was used to space, and it was used, the water that was produced from the fuel cell, it was used for consumption. So fuel cell has been around for very many of years. But with the years gone by, there has been problems with the fuel cell, which needs improvement. Like every other technology, the technology is established. Then we look at what are the challenges of the technology that needs improving. Major product or major problem in the fuel cell comes in the what you call the membrane electrolyte. As you can see in the fuel cell, we have methanol solution. This side can be methanol, this side can be hydrogen, this side can be ammonia. It can be any hydrogen-rich solution that should be used as a fuel. But we've chosen methanol as we are aware that methanol is a very renewable material. In South Africa, we're one of the highest producer of sugarcane, and we should be able to extract methanol from sugarcane waste. So this technology should be feasible to work in South Africa. We have the feed, we have the anode material, we have the cathode material, and we are developing the electrolyte material. As you can see, if you have a solution, it should go inside the anode and it should be catalyzed. When it's catalyzed, it produces what we call hydrogen or an ion. So it produces here in the membrane, and there is an ion should be able to complete the cycle. When we are still growing up and we're studying in underground program, this used to be called a salt bridge. If you remember the concept of batteries using salt bridge in your previous undergraduate studies, that's what the membrane is primarily want to reduce, want to develop. Historically, this membrane, it was never a membrane, it was a liquid electrolyte. And there has been many problems with liquid electrolyte, which we'll discuss at a later stage. So our research group is looking at this membrane and also as a whole, what you call membrane electrode assembly. If you zoom in this section, which is a membrane, this is what you see. You see what we call a diffusion layer, we see what you call catalytic anode, we see what you call diffusion oil, right? But the main focus for our research is in the membrane. You can see the importance of the membrane. If you have a reaction happening on the left hand anode, you have a reaction happening on the cathode, you still have to have a hydrogen or OH minus passing through the membrane. If this part is not efficiently, you will not be able to get enough output. That's why we're calling it, this is the heart of the fuel cell. We know the heart does so much function within human bodies. So the membrane within the fuel cell is the heart of the fuel cell. If you get this correct, it should be able to have a working prototype which should be able to produce higher amount of output and higher amount of energy. When you look at the overall reaction as an anode, this is what you have if you have methanol. You have a total of about 6 electrons. Methanol is highly rich. So you can see how much of energy could be produced with the amount of 6 electrons. So going back to the membrane that we are working with as my group in the University of Johannesburg. The ideal membrane that is supposed to be used in the fuel cell, like we've mentioned, historically, we used to use liquid electrolyte. It could be sodium hydroxide, it could be KOH, and so forth. Any OH base liquid electrolyte was used. But now, based on many challenges that the liquid electrolyte forms, for example, if you're having a liquid electrolyte here, it's able to leak into the anode or to the cathode, then it corrodes all of this material. Then the electricity that is produced is less. Remember, the methanol is supposed to get catalyzed and produce electrons and also hydrogen. So if this is no longer able to function due to the liquid electrolyte, then your fuel cell is as good as dead. It can no longer be used. So we're trying to remove the water and add a membrane which won't be able to contaminate the catalyst. Ideally, these are the properties that the membrane should have for them to be used for fuel cell. it should have high ion conductivity, which normally is same as having a high ion exchange capacity. But you'll see through my research that we've discovered that it's no longer true that for a material to have high ion conductivity, should have high ion exchange capacity. There's been some research which indicated that a material can have low ion exchange capacity, but surprisingly have high ion conductivity. But the key part is that it's supposed to have high ion conductivity. It should also have low fuel permeability. Remember, we just indicated that if you have a liquid electrolyte, it's able to leak out and poison the catalyst. So whatever material, either methanol or hydrogen that you have here, when you have a membrane, the membrane should not also allow any material or any solution to pass through so that it cannot poison the cathode or the anode. So it's supposed to have low fuel permeability. It should not permit any fuel that you're using. And it should have moderate water uptake because you don't want flooding of the material. The fuel cell produces water, so the membrane should be able to absorb all the water and be able to function correctly. One of the key problems that the membrane suffers is what we call degradation. So the membrane is supposed to have moderate conducting sites degradation. So what are we saying? We're saying, number one, the membrane should be able to pass through OH minus. In our case, we're doing what we call anion exchange membrane. So our membrane should be able to pass through OH minus. This is what this picture is showing. Secondly, even though it's passing through OH minus, all the methanol or ethanol that you're using should be propelled out from the membrane. It should touch, yes, but it should not pass through. Only the oil should pass through. Thirdly, as I've indicated, one of the problems that membrane suffers is what you call degradation. This is the design of a membrane. So you have your polymer backbone membrane and you have conductive site. So you see there's an aromatic structure, then you have a nitrogen-based conductive site. If you put this in OH solution, chemistry tells you that this will degrade via Hofmann elimination or SN1 reaction or E1 reaction, which is chemistry that we studied in our undergraduate. And correctly so, that will happen. But we want a polymer backbone with conductive site, which will prevent that. If it does happen, it happens at a lower rate. So what product normally produce? If you have OH, you end up having these products, you end up having nitrogen-based component with methanol separation. Once your membrane degrades in this way, it's no longer effective. You cannot use it. You need to change it. Another method which hinders the membrane is the production of OH-based aromatic with amine-based product and so forth. So all of this is SN1, E1, and Hofmann elimination. If you remember those type of degradation, and there's nothing we can change with that. We just need to find a way of reducing the speed of this degradation. As the Department of Chemical Science and Johann Spec, the energy group, we are solely focusing on these 4 different types of membrane for our research. We're looking at polyphenol oxide, we're looking at the polyether sulfone, we're looking at polyphenol sulfone, we're also looking at polyphenylene isophthalamide. These membranes have high reaction rates. Remember, we want to take this material and add conductive agent. So we want to functionalize this material. So the membrane that I use, they're supposed to have a high rate of functionalization, which these polymers have. They also should be able to withstand chemical harshness. We'll be using different type of amount or different concentration of OH or KOH minus so that we can have OH that will pass through. So the membrane or the polymer is supposed to withstand those. It should not be degraded by those. Also, we want to use this material in higher areas of the sun. For example, when you look at South Africa, the highest that you can get in terms of light, it's about 35 degrees. So we want a membrane of fluid cell which will be able to also perform in those type of conditions in terms of weather. You go on the far north of Africa, you can get temperatures going to about 40 degrees. We want this cell to also work there. So we want a membrane which can also work in higher degradation temperatures. So this membrane fits that profile perfectly, which is why we are using them for our research. How do we make this membrane? Well, we have what we call the casting solution. This is the important part of our research. How do you make this casting solution, or how do you make these membranes? Once you've made this membrane, we're able to just cast them, then dry them, and be able to test them. Then this is what you call evaluation of a fuel cell. This tells you how much energy does your fuel cell produce. The biggest problem that we have is that if you have a catalyst, the catalyst or your material suffers from three stages. It suffers from what we call activation loss. It suffers from what we call ohmic loss. Ohmic loss is brought by the membrane. What is ohmic loss? Well, ohmic loss is the ability of the OH minus to pass through the membrane. So if the OH minus takes longer to pass through the membrane, that means you're going to have a high ohmic loss. If the OH pass through quick here, it means you have lesser ohmic loss, but you have higher ion conductivity. So this is related to ohmic loss. So if you have higher ion conductivity, that means this section is eliminated. But if you have low ion conductivity, this section is more, and it ends up reducing the amount of the output that you have. So since we are working on the membrane, this is the key part for us as material design for polymers or membrane in fuel cell. We want to eliminate this step when we are doing our performances, because the activation loss and the mass transport are mainly related to the catalyst. So that's a problem for people who are working on the anode and the cathode. For us who are working on the membrane, this is the biggest part, because the ohmic loss is caused by the membrane in the fuel cell or in the battery. So what have we done in our research group? Well, we've taken these type of polymers, we've functionalized them, then we use different type of nanomaterial, the material that we have in South Africa, embedded them, functionalized them, and also put them in the same system. Then have a look at, will this material improve these membranes, or will they reduce their activity? Well, fortunately for us, we've been able to publish different papers or many papers which indicates that these materials are able to enhance the performance of the membrane, which leads to higher output of the fuel cell. Looking at this paper, which we published in around about 2018, we indicated that if you have a PPO membrane, this is the membrane that we're talking about, this one, which is PPO, this one is PES, and this is PPS. So we've taken this membrane, we've blended with a polysulfone membrane, and we've also added what we call zinc oxide nanoparticle. Wanted to see what will metal oxide be effect when we're doing our fuel cell. Well, we propose that once we've done this system, we propose that if you're having the membrane system, you have these are conductive sites, the nitrogen based, that's why we're calling it quaternized. And you have OH minus pass through. If you have zinc oxide can act what we call as Lewis acid site, which means your OH minus is able to forge path on the zinc oxide. So basically the pathway of your OH minus to transport from the right to the left, remember it moving from this side to the side. It's no longer only using the nitrogen to pass through. Remember, this is OH minus, nitrogen are plus. So it does what we call a hooping method, keep on jumping and jumping and jumping and jumping until it goes to the left-hand side and completes a cycle. So we want this OH to pass through here quicker. We found out that if we add zinc oxide as part of the system, zinc oxide acts as Lewis base. What does that mean? It means it's able to accommodate the transportation of OH minus. So OH minus no longer only get transported by the nitrogen-based compound, it can also transported by the zinc oxide. And also, zinc oxide acting as a Lewis base, it enhances water uptake. Why is that important? Well, with fuel cell and the membrane, we have two transportation, which we're still going to discuss in details later. We have what we call a vehicular method, where this OH minus is transported through a membrane via the hydrogen bonding, and those can be happen in presence of water. And also what we call hooping method, which we've already spoken about. So what we found out was that ions are transported through a water molecularly bonded network due to the higher water uptake. And also hydrated membrane lead to higher ion mobility. Well, we look at the membrane that we've made. We look at the power performance of it. Then we did a comparison. As you can see here, the 1% and 2% zinc oxide membrane containing, it was able to give out at 80 degrees air conductivity of about 24 to 52. And during that time, remember, this paper is a 2017 paper. During that time, this was one of the highest ion conductivities that you get in this temperature. But you'll see, the more we've improved in this membrane, the more we're getting enhanced and very comparable ion exchange capacity and ion conductivity. Well, after we've looked at zinc oxide, as you can see, zinc oxide, it has one oxide, so it's metal oxide. Then when we decide to take a titanium dioxide, so this is a metal dioxide. The other one has one oxygen, the other one has two oxygen. So we want to see, will that make any difference? Well, theoretically, it's supposed to make different because the dioxide should be able to create bigger network within the water molecule, so which lead to better transportation. So we look at blending titanium dioxide with the same polymer. And once we got once, if you can see at the performances that you got, this table will show a comparison of the membrane that you did compared to membrane found in literature. As you can see, at 80 degrees temperature, we are able to get an ion conductivity of about 54 and 41. When you compare with other material in the literature, you can see that our membrane had one of the highest ion conductivity of its time. This was also a 2018 paper. So we were successful to say metal oxide are able to improve their membrane in terms of their conductivity. We also did what you call a voltage curve. This basically tells you if you have an open voltage and you're running time, will your degrade how much of the degradation will happen in terms of your open circuit. So basically, if you look at here, this was our OCV. It was run about 1. When we leave it about 60 hours, we can see that it degrades, but it still retains about 0.3. And this was one also the highest when you compare. Some material, after a few hours, it goes to 0, which means the fuel cell is not functional. So ours was functional. We also look at the same membrane, but this time around we added graphene oxide. We wanted to see what will carbon-based material do in this material. Remember, we spoke about the degradation of the membrane. We studied the degradation of the membrane. Interestingly, when we add graphene oxide, there was less degradation after 250 hours. If you look at this material, the one that you've done, you're looking at this material there, this color. You can see that after 250 hours, there was actually less than 10% of degradation. We started 100%. After 250 hours, our degradation was still above 90%. That tells that this membrane is able to perform at its highest level. So if you look at this graph, all of the membrane which had graphene oxide were able to retain more than 70% of their conductive site. Well, we took this membrane, we put it against membrane that are found in literature to see what will our performance be. Well, the important part what you need to look at is that we performed this study at room temperatures, while other researchers were performing this at different temperatures. Some perform at 80, some at 100 and so forth. We performed it at 25, which is room temperature. And we're able to get one of the highest outputs in terms of energy. This one, which has 2%, at room temperature, it's got about 112 milliwatts per centimeter squared. And when we compare to other material, which is this one, which had about 197, but bearing in mind that we had at 25, imagine if this was also performed at 80 degrees. Well, we did perform this at 80 degrees, and you'll see on other result that it actually went to almost above 200. So you can see from this comparing table that the graphene oxide was able to actually enhance. But if you look at this material that we've designed, we've taken a quaternized PPO blended with polysulfone, and we've taken a normal bare and functionalized graphene oxide, and it was still able to perform at highest level. So then the question was, what happened if we functionalize the graphene oxide and also put it in the same system? Well, we got a student to do that. This is what they reported. Basically, first of all, this is how they designed. They were using polysulfone instead of a PPO. So they designed polysulfone, they did what we call metallation, and they do quaternization. They use imidazole because we're able to see that if you have imidazole, it's able to be prolonged in terms of degradation. They performed this chemistry and they were able to get quaternized polysulfone. Then they took graphene oxide. Remember, we said in this paper the graphene oxide was never further functional. It was left as graphene oxide. In this case, we took graphene oxide, we functionalized it also with imidazole. So in this case now, we had a system which is both quaternizing. The membrane is quaternized, which means it's able to transport OH minus. The filler, which is graphene oxide, is also OH imidazole based, so it's able to conduct. So by virtue of looking at it, we're supposed to have high NH output and also high ion conductivity. Well, when we combine these two, we had a system which we end up calling it quaternized PS and blended with quaternized graphene oxide. Remember, these are the sites which conduct the OH minus when it's coming to the membrane. Well, we took this membrane after we've designed it. We took this membrane after we designed it. Then we wanted to see that once now you have this membrane, remember, this and this are quaternized. We wanted to see the transport system. Remember, on our previous slide, we said the membrane is able to be conducted here. And this membrane can be transported in terms of what? Water, and also in terms of hooping. What we found out when we quaternized both membranes, both the membrane and the filler in the study, was that the material, it now suddenly has two transportation of connectivity. Remember, normally the material is either going to have what we call vehicular transportation of OH, or it's going to have hooping transportation of OH. But we found out that if we quaternize both the membrane and also the filler, you put both transportation mechanism in control. Well, the material ended up having vehicular method, which means it's high water uptake. The water uptake is able to transport the OH minus. As you can see, this is how vehicular method happen. If you have graphene oxide and you have material design that are positive, it's able to have what we call hydrogen bonding. Remember, hydrogen bonding is not covalent bonding. It's basically static bonding, which is hydrogen bonding. If you have a hydrophilic and hydrophilic side, they are able, which means this line, your OH is able to get transported to, because it's OH. So if all of them are hydrophilic, so it's able to transport it. And also the hooping method was also part of the system. Hooping method happens if your membrane is covalently bonded to the conductive material. So if we have graphene oxide, then you put in our case, we put in imidazole. We ended up having covalently bonded material, which was part of amination. It was also able to conduct in terms. So basically now this membrane has two terms of transportation. And this type of transportation influence how the membrane lifetime is going to happen, and also influence the ohmic resistance, which influence the power output. Remember the ohmic resistance. Now keep that in mind why that is important. Well, we did some of this material. As you can see, this is the membrane PS without any graphene oxide. And all for this are also with increasing amount of graphene oxide. So the clustering that you see on the surface of this membrane are due to ionic agglomerization. It makes sense. You have too much ionic solution within the same place, so they want to stick together because all of them are hydrophilic. But that's partially good for us because these clusters, which are underlining to each other, they end up opening channels where the OH minus will pass through, making it quicker. And also it aids on fast kinetic and ion transport. And we then expect that the membrane will have or wouldn't have higher degradation. We also look at contact angle, we look at water uptake, but the important part I want you guys to see in this slide is the terms of ion conductivity compared to other studies. This ion conductivity, again, we did our membrane at 25 degrees. These are the two membranes we tried to show here. We did them in 25 degrees. Then we studied the ion conductivity. You look at the one with 0.5, it had about 73. The one with 1% had about 50%. When you look at the one with 73 and you compare it to the rest of the material, you can see that it's still one of the highest. This one, which is quaternized, it had about 112. They also did exactly the same thing that we did. They quaternized the membrane, they also quaternized the filler, which is why they're getting about 112 in terms of ion conductivity. So what are we saying? We're saying this membrane system, transportation of the OH minus by both the Grothman, which is a hooping method, due to imidazole graphene oxide, and vehicular transportation due to better membrane hydration for a longer period of time. Then this allowed different parts of OH minus transportation, thereby it increased the membrane conductivity. All of this is due to the imidazole function as graphene oxide, because we also did one without graphene oxide. As you can see on the water uptake, this section is the one without graphene oxide. You can see it's the lowest in terms of uptake. But the moment you add graphene oxide, you can see that the trend goes up, which means graphene oxide, it is actually working. Well, when you look at the final part with the degradation of the membrane, when you look at the degradation of the membrane, what I want you to have a look at this one. This is a 0.5. You can see that over 180 period of time, which is 7 days, this material is still able to retain above 60% of its original conductivity. When you look at the membrane without graphene oxide, it's able to retain only 30% after 7 days. So basically, graphene oxide, it does aid on the less degradation. But I want you to come back to this part. Remember when we spoke about the performance of your fuel cell, we said you have kinetic, we have 3 stages of losses, which is for us, we're focusing on ohmic loss. As you can see on this performance, we do not have any ohmic loss. We do not have an ohmic loss due to the membrane. What does that tell us? Well, this tells us that the membrane is able to move the OH minus faster on its membrane. So there's no drag. That's why we're not seeing any ohmic loss. As you can see, we had one of the highest output, which was above about 130 milliwatts per square centimeter of the power that we're able. So basically, quantizing both the membrane and the filler results to a combined transportation mechanism within the same system. This increased the ion conductivity and reduce the ohmic loss. We also did exactly the same thing, but this time we used what you call a ZIF, a zeolite imidazole material. We wanted to see how does it perform. We're using graphene oxide, now we want to see how does it perform. Well, we did exactly the same thing, but this time we did not functionalize the ZIF because the ZIF already contained imidazole, so there's no need to functionalize. The nice thing about the ZIF is that the imidazole is part of its original structure, so it's hard to degrade it. We functionalize, now in this case, we use PPO membrane, we functionalize imidazole. We also combine these two and made what we call a quaternized PPO ZIF-8 composite membrane. We also took it through the different stages of the characterization. If you look at the properties of this membrane, first of all, when you look at the ion conductivity and parts of the IC. Interestingly, when you have the ZIF oxide in this system, ZIF oxide produces very small amount of ion of IC, which is ion conductivity, but it produces a high amount of ion exchange. So now it's doing the opposite what the literature is telling us. The literature says these two are supposed to be correlatable, but in this case, it's not. Sometimes literature tells us that if you have high IEC, yes, you're acceptable to have low IEC if you have IC, but this material now gave us high ion exchange capacity and small amount of IC. Oh, this was interesting. Wanted to see how will this perform. Also, we continue doing different type of analysis. If you look at the same analysis, you can see this is the ZIF and this is the one without ZIF. The moment you start putting ZIF on the material, you can see then it starts showing different pathway on the surface because it's showing harsher condition. The moment you start seeing this spot and also these stretches, these are part of the pathway which is able to transport the OH minus of the ZIF. We did the performances of the ZIF. As you can see, the ZIF actually had higher output compared to the one which was functional as graphene oxide. The graphene oxide had high ion conductivity, but it had about 130 output. This window ZIF, it had lesser ion exchange capacity and less unconductive, but their performance was still high in terms of power output, which is what we want. When we took the ZIF and compared it to the same type of material in literature, this is the ZIF that we did, excuse me, the ZIF that we did, you can see the power density at 25. It has one of the highest power output compared to membrane of the same kind. This is the ZIF at 150. When you look at the same membrane, but now they've added silica, the same membrane and the same membrane, all of them have lesser power output, but the ZIF has higher output. What are we taking here? We're saying the ZIF is able also to increase the properties of the membrane and render the fuel cell very efficient. This is the two comparison system that we have. This is the system which does not have nanomaterial, the system which has nanomaterial. As you can see, this material pass OH minus in terms of what we call the hooping method. So it keeps on jumping until it comes to the side. But the moment we have the one with nanomaterial, this will be main nanomaterial, the green one nanomaterial. The membrane is able to fast track the transportation due to the presence of OH. Why? As you can see, the nanomaterial is able to align the transportation pathway in terms of the transport. So basically, it creates a clear path for H to move, which is why it takes lesser time. And this aid on lower permeability of membrane, also high performance. Well, we're not the first people or the only people who've reported this type of mechanism. This is the work which was done by Golubenk in Russia. They were also looking at how does nanomaterial affects the ion exchange membrane. They also reported the same thing, that if you have, this is the normal material, the moment you add nanomaterial, for example, here they're adding zirconium oxide, it's able to align the pathway within your membrane or your ion exchange membrane. You add SiO2, it's able to also align. This will lead to better ion exchange capacity. As you can see, this is random, so your transportation is delayed. Whereas the moment you add nanomaterial, it is increased. Well, we looked at this and say, these are the membranes that you've been doing. So let's go and have a look at what will happen if we add this different type of nanomaterial on Nafion. Can we improve Nafion? Well, we went and took Nafion, we added sulfonated zinc oxide on the Nafion. As you can see, the performance of Nafion, we were able to get about almost 200 power density when we're using zirconium oxide, which is a metal oxide, based on the properties that we've already spoken about. So this nanomaterial was able to increase Nafion. Well, we went a step ahead. We look at Nafion, we said, let's add zinc oxide based nanofibers. You know, nanofibers have high conductivity, can also have higher transport system. As you can see, this is also the study that we've made. We had a power output of about 69, which was also one of the better, or in terms of output, when you have Nafion alone. So we're saying nanomaterial works. We also went and looked at the proton conductivity, also and on of Nafion, but in this case we have zirconium and we added phosphoric acid, so we phosphonated it. When you look at the conductivity of the Nafion alone, this is Nafion 117, it was about 0.07, but the moment you add different time of zirconium phosphate, you have increase. This is the output of the material. If you can see, the highest, which is the red one, it was above 200, their output, whereas the one without nanomaterial, it was about 120 in terms of the output. So zirconium phosphate do work in terms of fuel cell. What are we concluded in terms of the fuel cell that we've managed to do? Well, like we've said before, this is the output graph of every fuel cell. Activation energy happens on the catalyst. Mass transport also happens on the catalyst. Ohmic loss happens on due to the membrane. When you look at the material that we've designed and we're doing the output, this is the consolidated output. We never have the ohmic loss. What does that tell us? It tells us the nanomaterial improve their membrane in our research. We do not have ohmic loss because there's fast kinetic within the membrane. OH minus pass through the membrane quicker, that it does not create any drag or any loss of power due to the membrane, as you can see in this membrane. We still have ohmic loss, we still have mass loss, which are related to the catalyst. Then that's all part of the material design in terms of fuel cell. Then we want to look at the metal oxide. This is a new research in our group, and this research will be in conjunction or in collaboration with Prof Kinwa from Thailand University, Chulalongkorn University. So this is part of the work that we're still doing. We're working on a membrane, and we're hopefully going to be sending some of the membrane to his lab so he can start testing and having a look at how do they perform when they are in metal battery. Our resources for now are able to only look at the properties of the membrane, but in terms of performance, we'll be sending some of the students to go to his lab and have a look at how do they perform with it. But we are happy to report very good results when it comes to this. But again, why are we doing metal battery? Well, first of the battery that we're doing is aluminum battery. We are in South Africa. In South Africa, we have high amount of aluminum. We're one of the highest producing people of aluminum in South Africa. Aluminum batteries has cathode which may be made of silver-based catalyst, and it helps lock CO2 by allowing. Remember, we're saying aluminum A. It basically means you have an anode which is aluminum, and on the cathode you have normal air, the one I'm breathing now, the one that you're breathing. That air is the one which is able to make the battery function. When you're looking at the chemistry of it, it has a total of about 4 electrons which are transported within the membrane, which means it's able to produce heat. So why are we doing this aluminum battery? What is the problem? Well, the problem about aluminum battery is that the moment you have, remember, the moment you have an electrolyte, this is an electrolyte, so even this one has an anode and electrolyte. All of these electrolytes are liquid. So the moment you have a liquid electrolyte, the pure aluminum or yellow aluminum is corroded by this electrolyte. So the moment this liquid electrolyte touch any type of material, can either in the cathode, they get covered. So it covers the surface, then it's rendered them less functional. So the hydrated alumina, then it creates what you call a gel-like substance, which is no longer able to have electric output. Our solution is to replace the liquid electrolyte with a polymer electrolyte that will have higher ion conductivity while retaining the water. One of the students is working on this material. So what I'll be talking about is part of his results. When you look at aluminum production in South Africa as a whole, South Africa in 2020, we produced about 707 tons of aluminum. Remember, ton, 100,000 metric to about 1 million kilogram. So we produce about almost 1 million kilogram of platinum. We're the largest aluminum producer in Africa, which is why then as a South Africa, we have what we call South African Aluminum Industrial Roadmap, which indicates that aluminum sector is a key element of South African industrialization, and it needs to be taken quickly to be able to have an aluminum-based market in South Africa and also in Africa as a whole, and also be able to take this industrialization and give it to the world, since we are part of the biggest producers of the aluminum in South Africa and also in Africa. What are the properties of metal battery that you are working on? Well, for now, we're presenting on aluminum battery. Later, another students, I will be presenting her work where she's doing iron battery. Aluminum battery, unfortunately, are what you call primary batteries. I'll tell you just now what does that mean. But for now, we want to look at the properties of metal battery as a whole. When you look at their theoretical energy density, it's very high, which means it's able to store energy and produce energy at a higher speed for a longer period of time. The last thing about them, they have high energy density, they're clean, they're simpler operation, and they use air as part of its material and use cost-effective material. For example, aluminum. Imagine a battery which uses aluminum. Changes most of you dispose aluminum this morning. You drank a can of Coca-Cola, you drank a can of Pepsi, you throw away the can. That's an aluminum-based can. So we use aluminum air because they are a cheaper component. What's the difference between a primary and a secondary battery? Well, a primary battery is a battery that you use, you throw it away. Whereas a secondary battery is a battery that is rechargeable. So the aluminum battery that you're using won't be rechargeable, same as other different types of battery that you find in the market. Once it's depleted, you throw away, you buy a new one. Then we have what we call a secondary cell, which is secondary battery. The one which after depleting, you charge it. The one that your cell phone is using now. The one which your laptop that you are listening this presentation on is working on. So it's a secondary battery. We actually want these kind of batteries which are secondary, but also you want primary batteries for traveling purpose because you wouldn't have a charging station. So these two types of batteries are actually very important to everyone anywhere in the world. Well, with the same thing about aluminum batteries, we're taking this membrane, as we've indicated that they have liquid electrolytes. We're taking this membrane and putting additional nanomaterial and see how their performance is. I've already explained what this figure means to you. So we're replacing the electrolyte, which is normally aqueous or organic solvent or just ionic liquid, and we're taking this and replacing it with a membrane which has nanomaterial. We've already indicated that the moment you have a nanocomposite membrane in this type of system, they have faster hydroxide transport, they retain water, they prevent hydration of aluminum oxide, in this case, in the aluminum air battery. And aluminum are corroded by the electrolyte. If you have a liquid electrolyte, they are corroded. But this will be avoided if you have a membrane. And they're going to have constant electricity output because now they no longer have a liquid electrolyte. The student looked at using polysulfone and what you call an zeolite, blending these two materials together and have a look at what happened, what type of chemistry happens, and what type of properties will this system have. Well, they blended polysulfone, they blended the CSM5 zeolite. The reason we chosen this zeolite is because they have high surface area, which means you are able, there will be higher transport. And naturally, they're hydrophilic, which means they are able to work perfectly with the transportation of OH minus. And they have good thermal and mechanical stability, and they're highly conductive. This is what the student did. They also took the material, did metallation, quaternization, then they had the final structure. They also took, made the zeolite up to, this is the type of zeolite. When we blended these two, this is the real membrane picture, a freestanding membrane that he was able to get. When we took at this membrane, we're looking at the properties. As you can see, this membrane has smoother surface and even distribution of ZSM5, which means they are very compatible. What would make sense why they're compatible? The zeolite is hydrophilic, the membrane is hydrophilic and has some parts of hydrophobic. So hydrophilic plus hydrophilic, it gives a homogeneous mixture, which is what you are seeing in the surface. Well, we look at the properties. We look at, importantly, the water uptake. Remember, we said we want a membrane which is going to take the water, so that the water will not leak to the anode, so and the anode to get corroded. Well, you can see that at different temperatures, the membrane is able to uptake enough water, so we won't have that problem. We also look at SL, which is swelling ratio and linear expansion. Interesting on this one, we expect that if the material absorbs water, for example, if the material was this thick, it absorbs water. It's supposed to be this thick, right? That's what swelling ratio means. If it's this thick, it absorbs water, it becomes this thick, like a tissue. But this material doesn't do that. What is that? It has what you call a linear expansion. If it absorbs water, it doesn't increase inside. Actually, it expands on what you call a linear. As you can see here, you have a linear expansion. Then instead of the material increasing inside, it actually expands this way. Why is that good? It means the moment it expands this way, it reduces the thickness of the membrane and it's going to have fast kinetic of OH minus. That's what we're able to find on this material. We look at the properties of it in terms of ion exchange and also hydration. One thing I want to draw to you is look at the ion conductivity that this membrane able to get. The real percent was able to get almost 230 ion conductivity. This is one of the highest conductivity you find in literature. As you can see, previously, we've been reporting ion conductivity, which is less than 100. But suddenly, this material gave us material which is above 220 ion conductivity. Why is this? Well, it's what we've already explained. Instead of the membrane swelling ratio to increase, it makes this membrane smaller. So it stretches out, which means it aligned the membrane correctly for faster ion transportation, which is why we're able to get such a high ion conductivity. We look at the degradation of the membrane. If you can see the membrane, it was able to withstand from 100% after 7 days. You can see the one with nanomaterial, they were able to retain above 60%. Also with the one without material. So this is good. And also this, we still want to do it over 2 or 3 months and see how it performs. Another one, the last section of our presentation is ion air battery. With the ion air battery, we're also doing the same thing. You have an ion anode, you have a liquid electrolyte, then you have a battery. We want to replace the liquid electrolyte to have better ion. Well, the ion air battery, like I've mentioned, is composed of ion on the left-hand side. It's normally grounded powder that is there. We'll discuss on why then we need to change this to a membrane because of that. Like we've mentioned, ion, it's a raw material, and that is good. You can find ion anywhere. And this battery works on an interesting aspect. It works on rust. So it basically for it to work, it's supposed to rust. So you rust it, then remove rust. You rust it, remove rust. Rust it, remove rust. When you are doing that, you're actually creating electricity. The problem is I indicate it because it also have a liquid electrolyte, So we want to reduce that. Why we want to remove that? Well, if you have liquid electrolyte, there are three things that happens. First of all is the formation of dendritic growth. If you have ion here, anode, which is grounded powder, and you have liquid electrolyte, with time, this liquid electrolyte comes into the grounded powder and it makes what you call dendrimers. So most of this liquid, when it comes in, it ends up forming this type of orientation. And this is bad because this short-circuiting, and this part indicates that the OH will no longer be able to be transported. This is the dendrimer growth, which we do not want. This normally happens at the solid electrolyte interface. So we want to make it a solid electrolyte interface. To avoid this, this is due to water. Another thing that happens is agglomeration. If you have water here, water-based material, and you have anode, and remember this is powder, the water is able to fuse all of this material and make it agglomerate. The moment it's agglomerated, we all know that it no longer have better function or no longer function the way it happened. Also, what ends up happening is that this liquid, it dries up at a higher temperature. So these are the basic problems which are affecting the ion air batteries. We want to bring a solution by removing the liquid electrolyte by using a membrane electrolyte. Same thing the student, what they're doing, they're using sulfonated PPO. Now we're using proton-based material instead of OH. So we want to transport H+. We also, in this case, we're using sulfonated graphene oxide. So we are blending these two materials, the membrane and also the filler. This is the freestanding membrane that the student was able to obtain. You can see the surface is very smooth and it was very strong if you're looking at with your naked eye. When you look at the SEM, wanted to look at the distribution of this material. This is the normal graphene oxide, this is the sulfonated graphene oxide. Then we took a space here, we did what we call element mapping, and you can see that it's perfectly distributed. You're looking at the carbon, looking at the oxygen, looking at the sulfur within the material, it is perfectly distributed. That means you're going to have better ion conductivity. Is that so? Let's have a look at the other result the student was able to get. When you look at the water uptake was good from 25 degrees to 80%. We have higher water uptake, which is what we want. Remember, we don't want any water going to the ion material because it's going to create dendrimers or it's going to create agglomerization. We have linear expansion. The same thing which I've just explained happened in the students. Instead of the membrane getting bigger, it actually stretched out. That's why you see higher linear expansion, but you see negative swelling ratios. What was the properties? Well, this membrane also had one of the interesting properties in terms of proton conductivity. These are the different type of membrane. You remember, initially there was a part where I presented the proton conductivity of Nafion. So look at the proton conductivity of the Nafion material compared to the conductivity of the material that you got J. If you look at Nafion, it normally gets at about 0.0 something in terms of their conductivity. But when you look at this material, it had even a 2.31 conductivity. So basically, if you look at the ratio in this, it is very high compared to Nafion. So basically, this membrane can actually replace Nafion. Historically, we've been saying we're using Nafion because they have high ion conductivity. This membrane has proven to have one of the highest ion conductivity when you look in literature in terms of the proton conductivity. Nafion 117, in our research, we found out it has 0.01. This is 30 degrees, and this is 60 degrees. And this is at 25 degrees, and it still has one of the highest, even at low temperature. You can imagine what would happen at very higher temperature. We also look at the properties of this material in terms of degradation. Interesting also happened, which we're still looking at. This material degradation was done over 7 days. We also want to do it over 1 month, 2 months, and 3 months to see how do they work. But what we found out is that if you normalize all of this, you find out there's no degradation that's happening. Instead, it's telling us that there's enough water uptake, which means there's high salvation process, which means there's high amount of uptake of the OH. That's why you see it's increasing. So instead of the ion conductivity to decrease, it actually increased because the membrane is able to accommodate enough water and actually increase the ion conductivity. Then the OH assume ion conductivity. But this is we are able to say this if we leave the material in an OH solution for a longer period of time, that the OH actually does not degrade the membrane, it actually accept it and leave it on the system. So in that note, in everything that you've presented, I want to acknowledge all the students who've done this work, because like I've said, I hardly do this work. It's the student who go to the lab and I just help with interpreting the results. I want to thank the collaborators of this work who have been very helpful in the work with that. We also want to thank Chulalongkorn University for the invitation, University of Johannesburg, and also the NRF for funding. Also, thank you to all for listening and also for participating in this series of workshop. Thank you very much. I'll be taking questions now.
I like your idea that you start develop the motivation by looking what you have in your country. I mean, resource you have in your country and develop the technology based on that available resource. Okay. Do we have any question from the floor? If the audience have any question, just type in the chat box. Okay, I read from the chat box and then the the presenter will address your question. Okay, and from we have one question on the. Can you read from the chat box, Professor?
Okay, thank you so much for your answer. I'm wondering about aluminum air battery slide 28. Why the air cathode which made of silver-based catalyst can help to block CO2 but allow to enter in the electrolytes. Thank you. Well, when you look at it has to do with the chemistry of the let's look at the chemistry of the battery itself. When you look at the size of the OH and size of the CO2, they're of different sizes. So that's why it's able to allow the OH and also reject the CO2. Also, when you look at the terms of their orientation, you know that CO2 is a linear and also O2 is a linear, but O2 is tetrahedral. So it's able to accept those one, but also reject O2. Also, itself, it does not have affinity to CO2, so it will reject something that does not want to be partnered with. It will only accept the O2. That's primarily the reason why it's able to accept O2 and reject CO2.
Okay, we also have another question from Aswin in the chat box, please.
Okay. Another question is, I would like to ask, based on the QPS data with imidazole, the maximum GO concentration is 0.5. After using 1%, there is a decrease in the percentage of ion conductivity. Why does that happen? Well, the easiest explanation of why this happens is because, remember, for any nanomaterial that you add in the system, they reach a threshold where they work as nanomaterial. Above that threshold, they no longer work as nanomaterial, they work as macromolecule. So they cluster around each other and rejects the nanomaterial properties and work as macromolecule. Thereby, they will no longer be able to give the properties of the nanomaterial, which is why then they are no longer able to conduct the OH minus better compared to the other one. So basically, based on that, we're able to see that the moment you go on 1%, the material is clustering in terms of the nanomaterial. So the nanomaterial are no longer working to their maximum core because there are already too much of it. So the threshold is 0.5. Well, we're not sure if you do 0.6, 0.7, 0.8, if they'll be better. But we can see that the moment you go to 1%, they decrease in terms of property. GO no longer have its GO properties.
Any more questions? Well, it's good to hear that you also study aluminum air and also iron air batteries. Those two systems actually are very difficult, from in terms of passivation of the anode, especially for aluminum. Well, I see that you work with alkali electrolyte. That alkali electrolyte, you will have problem of corrosion, right? HER very strong in alkali electrolyte. Yeah. In some case, I think the problem will be subtle by using salt. Yeah, I mean for such as sodium chloride or potassium chloride, especially in, well, if you can use seawater where it contains a lot of sodium chloride, right, as an electrolyte. Yeah, but of course, you by introducing the new electrolyte instead of alkaline electrolyte, that, well, we have problem of the, what is it, the decreasing of the activity of the air cathode, but well, it's a trade-off, well, because in alkaline electrolyte, the activity of OR activity is good, but well, we have severe problem of the corrosion of the aluminum. Yeah. That's my point.
Well, that's the biggest problem, and that problem is normally created by the liquid electrolyte. So once you see, if we replace that, would we have the same corrosion over a period of time, or we have less, like you've indicated? We need to have a trade-off at some point. We need to understand that if we need to find a harmony between the system that you are making and say, you know what, it's okay, I can lose the longevity of this by increasing this one. But what we don't want is to have one material performing way higher than the rest of the membrane. So we need to find a synergy within all of this material for the production of better output.
Yeah. And if you, well, actually, if you study the aluminum air battery, magnesium air battery also, well, share the same characteristic with aluminum air batteries. Yeah. And I think in some cases, magnesium air, it's easier to handle. Yeah, but of course,
Yeah.
use a lot of aluminum, maybe, well, that your interest. All right. And the other thing is that iron air also difficult, very difficult. Yeah, with zinc. Because of
Well,
passivation.
the ion battery would be better, but I think the ion air battery is even better in terms of the power output. If we are able to get material design correctly, we should be able to get better output in terms of the energy produced by the battery.
Yeah. But compare with zinc air battery, well, iron air, we have problem of the passivation, because iron has strong passivation. Yeah, the passivation, deposition of iron oxide on the surface of iron.
On the surface,
Right. Yeah. Then.
Well, like I said, anyone interested could always request this material. Then they will use them. Then we'll have a look at what kind of results that they were able to get. We are very happy to donate.
Yeah. And one of our colleagues work with flow battery, zinc iron flow battery. Well, we use in zinc as the anode, and for the cathode we use iron 2 plus, iron 3 plus instead of a iron metal. Yeah.
Iron metal.
Yeah. Instead of iron metal, we use iron instead. Yeah. So at the cathode, it's Fe2 plus turn to Fe3 plus, something like that, and can be converted. But for that system, it's good actually in terms of chemistry. But well, from practical, we need membrane. We need membrane to prevent iron to cross over to the other.
Practically all the systems need the membrane also to avoid the electrolytes leakage, because that's one of the biggest problems, the leakage of the electrolytes. So the moment you have a membrane base, that's guaranteed that's done longer. And also the poisoning of the anode, forming dendrimers and accumulating. The membrane does not have or remove all of those problems. So it is good that we're exploring that to see what is the best possible solution going forward.
Yeah. Okay. Wow. When in the future, maybe, we will be in contact, and then we can collaborate in these membrane with different system. Of course, system require different things.
Let's hope next day, January, the rate of COVID spread would have been lower, then the student will be able to travel within the countries.
Okay. All right. Any more questions from the audience? Don't be shy. Just if you have any questions, just type in the chat box. No more questions? Okay, of course. Well, I think Professor Msomi, we're not, well, uh, can be reached later. Okay. I hope you don't
Yeah,
mind, right?
no.
For the
Everyone who have
follow-up.
any question can always
Yeah.
email me if they
All
have
right.
questions.
Okay.
Yeah.
Okay. If you have
Okay,
any,
I'm adding my email on the chat box. So if you have any questions other than that,
okay, that would be
which you
good.
prefer to ask, just
Mm-hmm.
ask.
Okay.
Yeah.
Yeah. Everyone
So
see
any questions.
the email right in the chat box. So just copy it.
And also, just in addition to this, I know this is an energy seminar, but if there are people also working on desalination, this membrane, we're also testing them on desalination because we want to get to a point where we have one membrane which is universal. One membrane can be used in metal battery, one membrane can be used in fuel cell, membrane can be used in
Right.
water distillation, and so forth. So there are students who are working on the same membrane, but
Yeah.
in desalination and water
Yeah.
research. So you just want a universal membrane. So you can also request this kind of membrane, regardless which
Yeah.
field you are working on.
Yeah.
Let's have a look at how would
Yeah.
be perfect.
Custom made, right?
Yes.
Custom made. We list well property we want and then discuss with you. Well, to
Yeah.
yeah.
Okay, no problem.
Okay, thank you very much for today talk. And well, later, well, I'm going to compile the video and then post. I hope you don't mind to if we your this video on the YouTube. And of course, I will send
No
you the link.
problem. No problem.
Okay, thank you very much.
No problem.
Thank you, and take
Okay.
care. Okay, and everyone
Okay. Thanks a
enjoy
lot.
the rest of the day.
Yeah.
Bye bye. Bye bye.
Yeah. I know in Thailand, you guys in Thailand, you're going to bed now because
No,
it's
no,
late.
no,
It's
no.
late in the afternoon.
Wow, just 4 o'clock. 4 o'clock. Yeah, in the afternoon.
Oh,
Yeah,
okay.
we still have
Okay,
time.
but have a good afternoon, and the one in South Africa, have a very good day.
Okay. Yeah.
Okay.
Okay.
Bye bye. Have a good day, everyone.
Okay. Take care. Bye bye.
Bye bye.